As a metal cools, its temperature approaches that of the surroundings, and the rate of temperature change can be modeled through the differential equation described by Newton's law of cooling. Utilizing this formula, the time it takes for a metal to cool to an ideal temperature can be found, even if that temperature and its initial temperature is too high to be measured through the use of analytical apparatus. In this example for I, rearranging the equation so that all the temperature variables are on the same side allows us to integrate both sides of the equation, the left-hand side becoming a natural log and the right-hand side becoming a linear equation of time t, with the constant of integration as shown. However, as we are discussing the cooling of a metal, we can assume the surrounding temperature is lower than that of the metal, so the absolute value sign is unnecessary. Substituting time equals 3 hours and temperature equals 210 degrees, then manipulating the variables gives this equation, with 3 unknown variables k, c, and a. As this expression alone cannot find the time taken, we must substitute other values of temperature and time that are known, which are time equals 8 hours, temperature equals 80 degrees, and time equals 13 hours and temperature equals 40 degrees, to form 3 simultaneous equations as shown below. Manipulating them to find the value of the constants, we have now determined a specific function which shows the temperature over time, and substituting our desired temperature gives the time it will take, 1 hour and 20 minutes. For part 2, the rate of cooling can be found simply by substituting the temperature, 300 degrees Celsius, and the constant values to find that it is cooling at 65.556 degrees per hour, suggesting that the metal should be worked with quickly once it hits this temperature, as it is rapidly cooling and hardening. For part 3, we begin by trying to find the temperature of copper, rearranging the differential equation again to have all temperature variables on one side, then integrating, then removing the absolute value sign once again, as the metal's temperature is higher than that of the surroundings. We are given that the surrounding temperature is still the same, and the K value is 1.3 times the K value of iron, so we can determine the values of A and K as shown. However, the value of C is still unknown. Thus, substituting time equals half an hour, temperature equals 250 degrees, then rearranging, C value is found to be 5.582. Now substituting T equals 0 gives initial temperature of 287.824 degrees. After finding the initial temperature of iron by substituting T equals 0 into the equation for temperature of iron, we find its initial temperature equals 403.298 degrees, so we can finally find their initial rate of cooling by substituting temperature as initial temperature into the differential equation for the rate of temperature change, and substituting their respective constant values of A and K as shown. Thus, by comparing these values, we can see that the iron was initially cooling at a faster rate than copper.
Created using Powtoon.